Greetings and welcome to the Chapter 7, Section 7.1 lecture for Chemistry 150. In this section, we're going to introduce the chemical reaction. We've been through the understanding of atoms, we built them up into molecules, and we saw how they can be named and how the formula has so many cool things. Well, we're going to take it to the next step, and we're going to look now at the chemical reaction. And if you want an analogy for this section, in the English language, people take the letters, 26 letters, and they build lots of words, and there are incredible dictionaries out there with massive numbers of words in them, which is really cool. However, sentences are really where things happen, all right? The words by themselves don't usually do that much. It's putting them together where things actually happen, to how I'm communicating with you right now, for example. And in chemistry, there is an analogy. Atoms are like the letters, all right? And the atoms combine to make compounds, which are like words, and the words are cool. But it's how the compounds interact with each other, what things they make or what things you need to make them, that makes chemistry interesting. And that's like the sentence, if you will, of chemistry. And in chemistry, we call those chemical reactions, all right? The chemical reaction is the action of the reaction. And anyway, we'll talk about things like that later, but this is a pretty cool section. It allows you to do a lot of things with chemistry instead of just looking at them and saying, "Ooh, how pretty." You can actually make things, do cool things with them. So let's get into it. But another analogy that you can use, if you don't like my letters to words to sentences idea, which is fine, chemical equations are kind of like recipes in cooking. And I'm not the greatest chef of all time, but I know enough that if I want to make a cake, I have to put in so much flour or eggs or water or sugar or whatever the heck goes in cakes. I don't even know. The things I put into the cake are like reactants, the starting materials, and the desired thing that I want, the cake, is the product. And chemistry is a lot like that in some ways. Just like in chemistry, if you want to make something, you have to have the right amounts, all right? Too much flour makes a cake dry, not enough flour makes it from even happening and stuff like that. Same things in chemistry. You have to have the right amounts in the right proportions. You have to use the right temperature, all those kind of things. Pretty cool. So in this section, we're going to learn how to create balanced chemical reactions. These will be like recipes that chemists could use to make things and stuff like that. It's pretty cool. And out of the recipe, we'll be able to make so much product. We'll be able to actually see how much product it is. As it says right there, don't lick the spoon in chemistry. In the kitchen, you'd be all right to lick the spoon more likely than not. But man, in chemistry, of course, this stuff's pretty crazy. But the analogy, all right, the analogy is good. You can make things in chemistry like with a recipe, and we're learning how to build recipes essentially in this section. Down the lower right-hand corner there is an example of a chemical equation, chemical reaction, chemical equation, same thing. And this would be a type of a recipe. Now, in this recipe, which isn't as appetizing as making a cake, by the way, anyway, we're putting in sodium hydrogen carbonate. And believe it or not, that's actually baking soda. If you have baking soda in your house, that's what it is. And the baking soda in this reaction, you're heating it up like you would a cake, and you're making sodium carbonate, water, and carbon dioxide. So we call the things you put into the reaction reactants, like the starting materials, and the products are things that you get out. So this is a chemical equation. And again, like I said earlier, reactants are just substances that you put into the chemical reaction. Products are the substances you get out of the chemical reaction. And just like if I say I'm going to bake a cake, that's the exciting product, all right? Usually the products are more exciting than the reactants, but not necessarily. But regardless, you can't have the products without having the reactants in the right combinations in the first place, all right? The reactants will be used up, the products will be created. And for our classes right now, reactants will always be to the left of the arrow, and products will always be to the right of the arrow. Here's another chemical reaction, this time between aluminum and oxygen, making aluminum oxide. And the numbers there in front in green, you can see, are quite different. And the numbers I'm referring to are the 4, the 3, and the 2. Those numbers are called stoichiometric coefficients, or just coefficients, and you don't have to be able to spell or say, for that matter, either one of those terms, but they're really important to chemists because it allows you to figure out the relative amounts of reactants you need for a reaction, and it also allows you to tell the relative amounts of products you're going to get out of a reaction. Another thing about that given chemical reaction there is that there's a little S, G, and S to the right of those things. And those refer to states of matter. And these are optional. They're not always included, but if they are there, it can be really helpful. Some of them are pretty easy probably to figure out, like S means solid, all right, and the G means gas. So oxygen is a gas, and the aluminum on the left and the aluminum oxide on the right are both solids. Sometimes you'll see L, which is liquid, and sometimes it looks like a cursive L, and sometimes it looks like a 1. Sorry about that, but that's what we have to deal with. The other one we'll see a lot, though, is AQ. That stands for aqueous, and that means that thing is dissolved in a solution. So you can have like a salt water solution, which is salt in water. You could write salt water as NaClAQ. So AQ just means dissolved in water. All of these things we're going to talk about here are dictated under what's called the law of conservation of mass. And all that means is that all the mass that goes in has to be accounted for on the way back out. This is an old school balance on the lower right there, where you have to have things balanced. And that's critical in this particular section. It would be so tempting many times to just put an atom or two under the rug, sweep it under the rug, or pull an atom out of thin air to make things happen. But that doesn't happen in chemistry. We must be accountable for all the atoms going in and all the atoms coming out. The bonds between the atoms are going to be rearranged, all right, to make new compounds, break compounds apart, stuff like that. But none of the atoms are actually disappearing, and you're not going to be making any new atoms. And that might seem a little strange, but that's really more like magic. If you're going to have atoms just disappear out of the thin air or appear out of nowhere, that's really like the kind of silliness, and that's not what science is all about. So in science, we must take into account what goes in and what comes out of a reaction. We're going to harp a lot on this section how chemical equations have to be balanced. And all that means is that the atoms on the reactant side to the left of the arrow must equal the atoms on the product side to the right of the arrow. That's incredibly important when it comes to chemistry. And we can play with the coefficients, those big numbers that go in front of the chemicals, but you don't want to change the actual numbers of atoms in the molecule. So for example, earlier we saw an Al2O3 for aluminum oxide. You wouldn't want to change that to Al2O4 if you needed an extra oxygen, all right? That doesn't fly. Remember from the nomenclature section that all those things are balanced for charges and having noble gas configurations, blah, blah, blah. So you don't want to change the little numbers in this section, but you can absolutely change the bigger numbers in front of the molecules. And we'll see how to do this here. So in a balanced chemical reaction, you're not losing or destroying any atoms. They're all accounted for. And the atoms on the reactant side have to equal the atoms on the product side. Now here's an example of making carbon dioxide, all right? And you're taking carbon and oxygen, which is a diatomic, have no fear of ice clear brew, and you're making CO2. Now notice the atoms on the bottom. You've got a carbon on the left and a carbon on the right. So the carbon atoms are all accounted for. And in the O2, you've got 2 oxygen atoms, and in carbon dioxide, you have 2 oxygen atoms. So the atoms here are accounted for on both sides. They're equal, 1 C on each side, 2 O's on each side. They've been rearranged. It's no longer oxygen connected to oxygen. Now both of the oxygens are connected through the carbon, and carbon's not by itself. So you're rearranging the way that they're interacting, but the atoms are going to be the same on both sides, and that's going to be the key to figuring out how these things balance. Here's another example. This is phosphorus, which is oftentimes P4. It's reacting with 6 bromines, and bromine is a diatomic, have no fear of ice clear brew. Brew is bromine, so there's 6 of those. And they're making a compound called phosphorus tribromide. And you'll notice here the coefficients 4 in front of the PBr3 and 6 in front of the Br2, excuse me, but P4 has like an invisible 1. We don't write 1s in front of the coefficient as a coefficient. Usually, we just assume that's there. If it was 0, you wouldn't have it listed there. So if it's there, it's there. So you can see that for P4, that means you have 4 phosphorus atoms and 6 Br2s. Here's all the individual Br2s. That means you've got 12 bromine atoms. Now for the 4 PBr3s, that means you have 4 times 1, 4 phosphorus, and 4 times 3, 12 bromines. So if you figure this all out, 4 P's, 12 Br's, and guess what? Balanced. 4 phosphorus atoms on both sides, 12 bromines on both sides. So this is a balanced chemical reaction. Now note that the coefficient multiplied everything after it. So with that big 4 means 4 phosphorus and 4 times 3, 12 bromine. That's the thing about coefficients. It's times everything that's past it, all right? Not just the P. If you follow these 4 steps, I think you can balance any chemical equation. So let's look at an example how these steps work out. So first of all, let's look at sulfuric acid reacting with sodium hydroxide, and it creates sodium sulfate and water. And let's say this was a reaction we wish to balance. Okay, so the first thing you need to do is you need to figure out what the formulas are for those chemicals. And this is again back to the nomenclature lab. Now, sulfuric acid is an acid. It's going to have the H listed first. And if you look back in your notes, it's H2SO4. Sodium hydroxide, sodium is Na. It's Na plus when it's with an ionic compound. Hydroxide, a polyatomic ion, is OH minus. So sodium hydroxide is going to be NaOH. Now on the other side, sodium sulfate, the first product, sodium is still Na plus 1. Sulfate is another polyatomic ion. It's SO4 minus 2. So when you figure that formula out, Na2SO4, got to make sure those charges all balance out, don't have anything left over. And water, you probably know, or if you don't know, H2O. So you've got to figure out what the chemicals are. Here's sulfuric acid, sodium hydroxide. On the product side, sodium sulfate and water. And again, if you're having questions on this step, you should go back to the nomenclature section. Make sure you're hip with those rules. This is why we're doing it, all right? We're getting to the point now where we can start making things. But if you don't know what you're starting with or what you're making, it makes it kind of tough. If you look at this equation that is at the bottom here, for example, there's 2 sodiums in sodium sulfate, but only 1 sodium in sodium hydroxide. So this is an unbalanced chemical reaction. Not all of the atoms are balanced. And you can probably also see that, for example, there's 2 hydrogens in sulfuric acid and 1 in sodium hydroxide, but we only have 2 hydrogens on the product side. So we need to balance this reaction. We need to take into account where the atoms are coming from and where they're going to. And you must have a balanced reaction in chemistry. So we're going to start putting coefficients around and try and make the atoms balance out on both sides. So let's look at the sodium first, all right? If we would put a big 2 in front of the sodium hydroxide, that would make the 2 from sodium sulfate, at least those sodiums would be balanced, because then you'd have 2 Na and 2 O and 2 H. But that would at least balance the sodiums. So this is a good way. And you don't have to start here, by the way. If you'd rather start somewhere else, it's okay. But in this case, let's start with sodium. We'll put a big 2 in front of that. And that does affect not just the Na, but it also affects the O and the H. So we're better. All right, the hydrogens still aren't balanced. We actually added hydrogen. I told you earlier there were only 2 hydrogens on the product side. Now we have 2 hydrogens here, and now we have 2 hydrogens there too. So there's 4 hydrogens on the reactant side and only 2 on the product side. So I think it's time for another coefficient. Now, one quick word here about polyatomic ions. If you can keep polyatomic ions together, do so, all right? So we've got one sulfate on the left in sulfuric acid and one sulfate on the right in sodium sulfate. So now this reaction is at least balanced for the sodium and the sulfate. But the hydrogens and the oxygens, not so much so. So if you check the equation to make sure that everything is balanced, definitely not. All right, it's definitely not balanced. Now, we're going to leave sulfate out, but you can see how you have two OHs and two H's there, all right? On the other side, we have just one oxygen and two hydrogens if you keep the sulfate out. So what that means is we need to put a big 2 in front of the water. And if you do that, then you have 2 leftover oxygens and 4 hydrogens, and that balances out the different pieces. Now at this point, this reaction is balanced. 2 NAs on the left, 2 NAs on the right. A sulfate on the left, a sulfate on the right. You've got 4 hydrogens and 2 oxygens. 2 oxygens, 2 hydrogens, 2 more hydrogens right there. This reaction is good to go. I'm going to put up one more little warning. Right now, we have like a 1, 2, 1, 2, if you look at the coefficient. So like 1 sulfuric acid, 2 sodium hydroxides, 1 sodium sulfate, and 2 waters. This reaction would also be balanced if you had a 2-4, 2-4 ratio. 2 sulfuric acids and 4 sodium hydroxides makes 2 sodium sulfate and 4 waters. This point just says always use the lowest whole number values. This reaction, as written, already has that. But if you had that 2-4, 2-4 ratio, you'd want to cut it down to 1-2, 1-2. Scientists like using smallest whole number ratios as many times as possible.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
This reaction, which has a lot of energy given off, is making an aluminum bromide compound. It's Al2Br6. Now, notice on the left side, bromine is 2 and aluminum is 1. And I'm going to remind you here about Hankel-Briff. This is something we talked about in the chapter 3, part 1. Those are the 7 diatomics. You could also use the have no fear of ice clear brew. Bromine is one of the 7. It's the Brr and Briff. It's the brew and have no fear of ice clear brew. It's one that does exist as 2. But aluminum is not one of the Hankel-Briffs or have no fear of ice clear brew. So notice here how aluminum is by itself, but bromine is a pair. And this is why those 7 are really important. We deal with those 7 chemicals a lot. So if you see one of them, you wouldn't write like just Br, you'd write Br2, or you'd write N2 instead of N, stuff like that. But anyway, in this problem, Al2Br6 looks like this thing right here, and we're starting with individual aluminums and also Br2s. And you can see here how there's 6 atoms of bromine on the right, and this has been conveniently drawn as 3 Br2s, which would be 6 atoms. And you've got 2 goldish aluminums on the product side, and that's why there's 2 aluminums right there. So when we want to fill in these coefficients, all right, we're going to have 2 aluminums because there's 2 gold atoms and 3 Br2s because that's how many bromines we need to make 1 Al2Br6. And you don't usually write a 1, but that's what you would do. And so when this reaction is written as balanced, 2, 3, and invisible 1 would be our coefficients. And that just lets the atoms on the left equal the atoms on the right. Everything's been rearranged, but you're seeing the idea. And again, also remember those 7 diatomics. They're going to pop up a lot.
In the combustion of propane, a single propane molecule reacts with 5 molecules of O2 to produce 3 molecules of carbon dioxide and 4 molecules of water.
This is an example using propane, and a lot of home barbecue systems will use propane. Sometimes they use butane too, but propane is good. Propane is C3H8, and when you're using a barbecue, propane combines with oxygen, and the products are carbon dioxide and water. This is called a combustion reaction, by the way. We'll talk about that later. But anyway, let's balance this reaction, and you can see just by looking at it that no way, this isn't balanced at all. One thing that helps though is that all of the carbon ends up as carbon and CO2, and all of the hydrogen ends up as hydrogen in water. So what I do when I do problems like this is I always start by balancing those parts first. So I would put, for example, a 3 right there by carbon dioxide because propane has 3 carbons. Now, water comes in pairs of 2 hydrogens, so if we have 8 hydrogens, that means I would put a 4 right there. The last thing I would balance would be the oxygen, because oxygen is all by itself, so I can manipulate that coefficient without messing up the other ones. And if you look at this long enough, you have 3 times 2, 6 oxygens from CO2, and 4 times 1, 4 oxygens from water. That would be 10 oxygens total. Because oxygen is a diatomic, I would put a 5 right there. So knowing that there's an invisible 1 by C3H8, the balanced reaction here would have 5 O2s, 3 and 1 C3H8. Those would be the reactants, making 3 CO2s and 4 waters on the product side. These are all gases. Again, that's nice to know. It's not really critical. If you don't want to put the states of matter in, it's quite all right. Here's a reaction we can balance. Calcium plus nitrogen makes calcium nitride. Now to do this, we have to think about a couple of things. We got to figure out the formula of calcium nitride, and we also got to think about those diatomics. So remember the expression, have no fear of ice clear brew. Nitrogen is the no, or hung, cold breath, I'm trying to emphasize the N. Nitrogen is a diatomic. So for nitrogen, we're going to put N2. Pretty sloppy, but it's hard to write this stupid thing. Anyway, calcium is not Hankel-Briff, not part of the have no fear. So that's going to be just Ca. And when these two come together, calcium is a group 2A fixed charge metal. It's always going to be +2 when it's with a nonmetal. And nitrogen, group 5A, is always going to be negative. 5 minus 8 means it's going to be -3. So when you figure out the formula for calcium nitride, 3 times 2 is 6. 6 divided by 2 means you're going to need 3 calciums, and 6 divided by 3, you're going to need 2 nitrogens. So the formula for calcium nitride, Ca3N2. So N2 is a diatomic. Ca3N2 is calcium nitride. Initially, we have just calcium by itself because it's not a diatomic. Because of the 3 calciums in calcium nitride, we'll put a 3 right there. We are good to go. If you get to the point and you don't feel confident that this reaction is balanced, one thing that I'll do sometimes is I draw a line through the exact middle of the compound. And on the line itself, I'll put all of the elements. Now, in this case, it's only calcium and nitrogen. And I'm literally just going to count the atoms on both sides. And if this is a balanced reaction, the numbers will match. So notice here I've got 3 calciums, so that's 3 on the left. N2 is 2 nitrogens. And on the product side, calcium nitride has 3 CAs and 2 Ns. Oh, they balance. If the numbers are the same on both sides, then they balance. So this is a balanced reaction. And if you're ever uncertain how to do these, I highly recommend you do this kind of test to make sure that it's working. Here's another example. This is an example with polyatomic ions. This is magnesium chloride and sodium phosphate, making magnesium phosphate and sodium chloride. Now, notice that phosphate is on both sides, and phosphates is one of the polyatomic ions. If a polyatomic ion is on both sides of the reaction, leave it as a unit. Don't break it down into the individual atoms, and I'll show you that here in a little bit. So, chloride, Cl -1, magnesium, Mg +2, sodium, Na+, phosphate polyatomic, PO4 -3. And for this problem, those are the same on both the reactant and the product side. So when magnesium chloride comes together, MgCl2. When sodium and phosphate come together, Na3PO4. The next one is kind of funky, magnesium phosphate, because there's a magnesium +2 and a phosphate -3. So to make that common denominator work, you're going to have Mg3 parentheses PO4 parentheses 2 and sodium chloride NaCl. So here's what that looks like. MgCl2 plus Na3PO4, making NaCl plus Mg3PO42. Magnesium phosphate is a solid. It's insoluble in water, while the other things dissolve in water. That's why they get the AQ symbol. That's nothing you need to know, but that's why those symbols are written. Now you can probably see that this reaction is not balanced. For example, we have 2 phosphates and only 1 phosphate here, and 2 chlorides on the left, 1 chloride on the right. Again, try and keep the polyatomic ions together. So let's try and keep that together. Let's balance out that first, because that's a big atom. So notice that if we only have 1 phosphate on the left and we need 2, we're going to have to put a 2 in front of the Na3PO4. And that at least lets the phosphates balance. Now, magnesium phosphate has 3 magnesiums, and magnesium chloride has just 1. So the other thing we're going to do is we're going to put a 3 right there. That'll make the magnesiums balanced. But now you can see you've got 3 times 2, 6 Cl's, and 2 times 3, 6 NAs. We're going to have to put a 6 in front of the NaCl to make that happen. So tentatively, this reaction looks balanced, all right? Everything looks okay, but you can always check yourself. So here's an example of what I did earlier. I drew a line down the middle. This is equals, same thing, okay? Notice how you should keep the polyatomic ions together, so phosphate on both sides, etc., etc. And sure enough, when you do this, they are the same right on. Now note, there's nothing wrong with breaking phosphate into phosphorus and oxygen, but it's a lot more atoms to count, and it's easy to get them confused. So again, I highly recommend keep the polyatomic ions together. This is a reaction where barium chloride reacts with sodium phosphate to make barium phosphate and sodium chloride, all right? And you can probably see again the polyatomics are not balanced. So we're going to hit that one first, and we're then going to go back and hit the bariums. This is a good one to practice. When you're done here, you should see that 3 barium chlorides and 2 sodium phosphates make barium phosphate and 6 sodium chlorides. And again, try and keep the phosphates together whenever possible. When you're balancing equations, only balance the atoms which occur in one compound on each side, all right? Balance the remaining atoms afterwards, all right? You always want to make sure those coefficients are the smallest whole numbers. And if you ever get in question, you can always do that check yourself at the end kind of thing, where you tally up the atoms on both sides and they should equal. Polyatomics, leave them together. Remember the 7 diatomics, Honkelbrief or Have No Fear of Ice Clear Brew. You should do good. So let's test yourself. First one is potassium and water making hydrogen and potassium hydroxide. This reaction, you can probably see, has 2 hydrogens on the left, and on the right, there's a H2 and a KOH. So there's 3 hydrogens. So this reaction is not balanced. What I would do for something like this is I would start playing with the different things. If you multiply everything but the hydrogen by 2, you'll be good to go. So 2Ks plus 2 waters makes H2 plus 2 KOH. The next one, barium plus what's called arsenic acid, H3AsO4, reacts to make H2 and barium arsenate. Arsenate is a polyatomic ion. It's not one that we've studied, but it is a polyatomic. It exists on both the reactant and product side. So try and leave that one as a unit. Don't break it up. So in this case, we're going to have to have at the least 2 H3AsO4s to balance the barium arsenate. When you do this and you play with the numbers, 3 bariums and 2 arsenic acids makes 3H2 and barium arsenate. The next one, PCl5 plus H2O makes H3PO4 plus HCl. So this thing's got some issues. You can probably see there's 5 chlorines on the left and only 1 on the right. So start playing with them. Make sure that they're working out. Notice the oxygens are also strange. 4 oxygens in phosphoric acid and only 1 in water. But if you play around with this long enough, you'll see that PCl5 and 4 waters making phosphoric acid and 5 HCl is a balanced reaction. And then finally, this last one is potassium chlorate, making potassium chloride plus oxygen. And we're going to do a lab with this reaction pretty soon. Potassium chlorate breaks down to potassium chloride and oxygen pretty readily. Oxygen, being a diatomic, has 2 oxygens, and KClO3 has 3. So multiplying those through by 2 and 3, you get 2 KClO3s, making 2 KCls plus 3 O2s. You are balanced. Practice, practice, practice. The more of these you do, the better. It gets pretty chill. Most people do pretty good on this, which is nice. But again, if you're having any questions on anything, you be sure and let me know. When chemists look at all the reactions known, there are some series of reactions which are very, very common. These 6 categories, I'm going to show you here in a little bit, are patterns that people see a lot when doing chemistry in the real world. And the advantage of knowing these is that a lot of times you can make predictions as to what the products will be without ever having done the reaction itself. So sometimes when people from like lower chemistry classes come up to me, they say, hey, what's going to happen in this reaction? And I'll say, oh, well, they'll transfer over like that. And they look at me like, oh, but really it's just my silly understanding of these reactions. So all my secrets revealed, let me show you the tricks of the trade. So again, these 6 reactions, very common, not by any means not the only types of reaction, but very common reactions. The first 2 are called combination and decomposition. In a combination, A and B are coming together to make AB, some kind of molecule, which is just the combination of both of them. Decomposition is kind of the opposite. It's the molecule AB breaking down to A and B separately. And sometimes in both combination and decomposition, you'll have 3 things making one thing, or one thing making 3 things, something like that. It doesn't have to be just 2, but hopefully you get the idea. In a combination reaction, you're making a more complex molecule. In a decomposition reaction, you're taking a complex molecule and breaking it down into smaller pieces. A single replacement reaction is kind of like a dance. So let's look at the first example right here with A, B, and C. So A and B are dancing, and C goes, hey, I want to dance with B. So C pushes A out. And on the other side of the equation, C and B are dancing, and A is by itself. This is a single replacement reaction where one piece is replaced by another. Now, the reason I have 2 examples right here is because you have to do it metals and metals or nonmetals and nonmetals. In the example I just showed you, A and C are both metals or positive, and they're going to trade places with each other. In the second example, X and Y are nonmetals, and they're going to be the ones replacing each other. So M was dancing with Y, now M is dancing with X on the other side, and Y is by itself. So the only thing tricky about single replacement is you have to have the same kind of species being replaced by a similar experience. Combustion reaction, we saw an example earlier with propane. There's actually a lot of these. In a combustion reaction, you're taking something organic, you're burning it in O2, and the products will always be carbon dioxide and water. which is kind of cool. The fifth kind and the sixth kind are actually more similar than they might appear at first. Acid-base is when an acid, where H is listed first, and a base, which is essentially a metal hydroxide, react. They end up having a type of a dance. H and M trade places. So M starts dancing with X, and H starts dancing with OH, which is H2O. So in an acid-base reaction, literally, an acid and a base react. Water is a product, and also MX, which is what we're going to see as a salt. Now, in a precipitation reaction, this is another one of these kind of things where A and B are trading dance partners, if you will. B starts dancing with X, and A starts dancing with Y. But in a precipitation reaction, one of the products is a solid. A solid in chemistry is called a precipitate, all right? And so if you make a precipitate, that's a precipitation reaction. I'm going to show you examples of all 6 of these, so hang tight. Let's look at them in a little bit more detail. In a combination reaction, 2 species, or even 3 species sometimes, come together to make a new product. And that new product is a combination of what you put in. The most common example, arguably, is when magnesium and oxygen come together to make magnesium oxide. Mg is like A, it's by itself. And O2, the diatomic, is B by itself. And notice here that the diatomics count as like individual pieces. But anyway, when they come together, they make magnesium oxide, a combination of the two. Now, because of the charges, all right, magnesium becomes positive 2 around oxygen, and oxygen becomes negative 2. MgO is the formula. It wouldn't be MgO2. You must think about all those rules we looked at in the nomenclature lab. So MgO is magnesium oxide, and then you can balance it from then by adding a 2 in front of the Mg and the MgO. Here's another example of sodium and chlorine coming together to make sodium chloride. And again, those dastardly diatomics are going to mess up all of our equations here. But in the last one, it was O2, and in this one, it's Cl2. So again, 2 sodiums plus chlorine making 2 NaCl. And remember, if an atom or an element is not on that diatomic list, it's going to be similar. Have no fear of ice clear brew. Of and clear are oxygen and chlorine, so those get a 2, but magnesium and sodium are not on this list, so they don't get a 2. You can also, though, do nonmetals, and nonmetals are covalent compounds with each other. This is sulfur trioxide reacting with water to make sulfuric acid, and that would be a combination reaction as well. Sometimes combination reactions are called addition reactions, which is fine. It's just another way to say it. Combination is the one that we'll use most of the time here. A decomposition reaction is where a complex molecule breaks down into 2 or more products. In this case, A and B are breaking down to A plus B, but it could break down to A plus B plus C. It kind of just depends on the chemistry. This is an example of a mercury oxide compound, mercury 2 oxide, and it's breaking down to O2, again a diatomic. You're going to get sick of me saying this. Mercury, the element, is not have no fear of ice clear brew, so it's by itself. You're going to need 2 mercuries and 2 HGOs. Mercury is a liquid at room temperature, so that's why the little L is right there. Kind of cool. This is the reaction we're going to look in lab later. Potassium chlorate, when it breaks down into potassium chloride and oxygen, that's a decomposition reaction. Again, something complex going down to something a little simpler. And because of the O2 diatomic, you need that 2, 2, and 3 in there. That's going to be an important equation for us later on. So let's classify these reactions as combination or decomposition, all right? And the first one there, H2 and Br2 are coming together to make HBr, all right? So 2 pieces are combining to make HBr. Combination reaction. The next one, aluminum carbonate, is breaking down to aluminum oxide and 3 CO2s. All right, you can probably see that that one complex piece is breaking down to 2 pieces. That's a decomposition reaction. And then finally, the last one, aluminum and carbon are making what's called aluminum carbide. Multiple pieces making 1 piece, combination reaction. Nice job. Single replacement reactions, all right, are again where two species are trading places that are similar to each other. And so in A and B here trading places, those would both be metals or positive ions. In the second example, X and Y would be trading places. Those would both be nonmetals or negative. And that's the only important part of this particular section. Single replacement reactions are somewhat similar, but again, make sure the metal trades with the metal or the nonmetal trades with the nonmetal. Here's a little picture version of it. A plus BC goes to AC plus B. And in this problem, A and B are the metals, C is the nonmetal, etc. You get the idea. Here's an example, an actual example of metals trading places. So zinc reacts with silver chloride to make zinc 2 chloride and silver. And what's happening here, zinc and silver, both metals, they're going to do the dance. Zinc's going to start dancing with chloride, and silver will be by itself. Now remember, all those charged things still apply. Silver and zinc are part of the stairs. Silver is +1, but zinc is +2. And since chloride is always -1, you're going to need 2 -1 chlorides to balance that +2 zinc, while silver +1 only needs 1 chloride to balance it. So you got to put a 2 in front of the AgCl and the Ag. Here's an example of the nonmetals. This is an example of bromine and chlorine trading places. So Br and Cl are both nonmetals. They're going to try and fight, I guess, over who's dancing with sodium, if that's the way you want to think about it. Anyway, bromine and chlorine are both diatomics, so Br2 on both sides, 2 NaCl, 2 NaBr. Sodium is still +1 on both sides. Let's do a learning check, figure out here what's going on. So this first one, zinc plus silver nitrate, wonder what happens there. So again, what we've got, zinc and silver, both positive, both metals, all right? That's going to be single replacement. If you think about what these are, zinc and silver nitrate, AgNO3. And zinc and silver are going to trade places. Like we saw earlier, though, zinc is a +2 metal. So nitrate being -1, you're going to need 2 nitrates to balance the zinc. And silver will be by itself. So because of the 2 nitrates, we'll put a 2 there and a 2 there. So yeah, zinc +2 silver nitrates goes to zinc 2 nitrate +2 silver. Woohoo! Again, the metals trade places. All right, and then this one, Cl2 plus NaBr. I'll write it up here this time so I won't have to erase it. Woohoo, getting smart. NaBr, chlorine and bromine trade places. You're going to end up with NaCl and Br2. Going to be 2s in front of that one. Good to go. A combustion reaction is a reaction super important in organic chemistry, and most of chemistry is actually the study of organic chemicals, biochemicals, stuff like that, which have a lot of use to them. Combustion reactions always start with something organic. You add oxygen, which is basically burning. Combustion, it means burning, essentially. And the products are always water and CO2, always. And like we saw with the propane example earlier, all the carbon ends up as CO2 and all the hydrogen ends up in water. So what I usually do on these is I first balance the CO2 and the water, and then I go back and do the O2, all right? And that works really well on these first 2 examples. So for the first one there, C2H4, you end up with 2 CO2s and 4 hydrogens becomes 2 waters, and you can balance the oxygen, and the same thing for the next one. Now, the last example is a little different though. First of all, sometimes reactants have oxygen in them as well, so it's carbon, hydrogen, and oxygen, and you've got to be super careful about that. These kind of things can get a little tricky. Sometimes you'll end up with a weird number of oxygens, but you can multiply it all the way through by 2. On these especially, make sure that you always have the smallest whole number ratio of coefficients. It would be easy on this one, for example, to get a 4 10:8:8 ratio, but you'd want to cut it down by half. So practice with these a little bit and stuff like that. If you've driven a combustion car with gasoline today, you have used a combustion reaction because gasoline is basically a combustion reaction to make our vehicles move. So a very important kind of reaction. There's also some chemistry techniques which make these kind of reactions really useful. We'll talk about those in the Chem 200 series. An acid-base reaction is when you have an acid and a base making water and salt. But what I want to talk about first is how acid and base reaction is sometimes referred to as a double replacement reaction. And what that means is that if you have A, B, and CD coming together, the A and the C will trade places. So A starts dancing with D and C starts dancing with B. And an acid-base reaction is this kind of reaction. The AB would be the acid, all right, maybe HCl. And the CD would be the base, maybe NaOH. And they're going to trade places, the H and the Na, because they're both positive. And on the other side, you'd have NaCl, all right, the leftovers from there. And the other species would be HOH, or water. So an acid-base reaction is actually a type of double replacement reaction. Sometimes double replacements are called double displacements. So in these acid-base reactions, you must have an acid with the H listed first. You must have a base, a metal hydroxide, and the products will always be water, H2O or HOH, and then some kind of a salt, which is the metal from the base and the leftover part of the acid basically coming together. Notice that a salt is not necessarily table salt, which is what we use. Table salt can be the product of hydrochloric acid and sodium hydroxide, but it really, in chemistry, a salt is a product of an acid-base reaction. Here's an example of nitric acid, HNO3, reacting with sodium hydroxide. And again, we know the first one is an acid because the H is listed first. Metal hydroxides make this a base. And again, the H and the Na are going to trade places. So HOH is water, and Na with NO3, sodium nitrate, that would be our salt in this reaction. And again, acid-base reactions are a type of double displacement, double replacement, or exchange reactions. These things have all kinds of things. We're going to see in the next part that precipitation reactions are also double replacement reactions, and there's other kinds too. But for right now, just realize it's like two dancing couples trading partners. All right, that's really the cheesy way to think about it, and it works out pretty well. Here's the classic acid-base reaction. Hydrochloric acid and sodium hydroxide making water and sodium chloride. Again, acid HCl, H listed first, base sodium hydroxide, a metal hydroxide, water being formed, and in this case, the chemistry salt is table salt. It's sodium chloride, the other product, all right? If the acid and base moles are equal, then it can be called a neutralization reaction. And in theory, if you have like equal moles that you're adding, then the products would be just water and a salt. So in theory, if you have hydrochloric acid and sodium hydroxide, and you've measured them super carefully, and you allow them to react, you should be able to drink the product, because it would be like salt water. Don't you dare try that, though, because I don't trust anyone's measurements enough to say with confidence that there wouldn't be some leftover acid or leftover base. And man, would your throat hear it. And if you look online, you'll find stories of people trying this before. They didn't do a good job. Their stomachs were all ripped out by acid and or base, so don't you dare try it. But anyway, neutralization comes from the fact that in theory, if the acids and bases are neutral, then you should have just neutral water and a salt, which would be in theory okay to drink. But again, you try it and I will disown you and I will be mad and I'll say your name lots of bad ways, so don't do it. I worry about my students all the time. So anyway, all right, Prophet, back on. Anyway.
When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, it splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form two molecules of water. Sodium and chloride ions are left in solution.
It's the formation of water, which is the exciting part in an acid-base reaction. The salt, sodium chloride, or whatever is left over, really isn't that interesting to science or to thermodynamic scientists, the science of energy. But it's the formation of water, and we'll see that. In the acid section earlier, we saw how acids make H plus or hydronium, and you can see the hydronium there, but it's really the H plus of the acid and the OH minus of the base that makes this reaction occur. We're going to come back to this subject again in Chem 221. It's pretty cool to think about. A precipitation reaction is similar to the acid-base reaction, except that instead of having water and some kind of salt being made, now you're going to make a precipitate. And a precipitate in chemistry is nothing more than a solid. So silver nitrate and sodium chloride will react. Silver and sodium are similar, so they'll trade places. You end up with Na and NO3 coming together, and the AgCl is actually an insoluble compound. It makes a precipitate. So this is a precipitation reaction. Now, at this level, you are not supposed to know if a solid's going to form or not. But if you see some kind of a problem where two chemicals are mixed and, oh, this solid was made, you can bet money that that's going to be a precipitation reaction more often than not. This is, again, another type of double replacement or exchange reaction where similar species are trading places with each other, dancing with new partners. This is, again, kind of a common type. So acid-base reactions and precipitation reactions are both examples of double replacement reactions, all right, where you wouldn't necessarily probably use double replacement, but you could use acid-base precipitation. The solubility of a compound is how much of the stuff will actually go into the solvent, usually water, before a solid begins to occur. And in this reaction, which is a precipitation reaction, lead to nitrate, PbNO3 is reacting with potassium iodide, Ki. It's an exchange reaction. The lead and the K are trading places. You end up with the charges. Lead is positive 2 on the left, it's positive 2 on the right. You end up with PbI2, a solid, and potassium nitrate. And it's the PbI2 which makes this reaction a precipitation reaction. When the solubility is exceeded, that's when you're going to have a precipitation. And we're going to talk more about how soluble things are, or how to make things dissolve in solution, or keep them from dissolving for that matter. But it's kind of fun to see how this stuff all fits together.
When we combine solutions of lead nitrate and potassium iodide, a colorful material appears. This is actually a solid called lead-2 iodide.
Lead-2 iodide is kind of a neat yellow color, as you can see right there. The solids are usually quite visible. The solids or precipitates look like cloudiness sometimes. It might be white. This is a neat yellow color, so it shows up really well. But even a little bit of cloudiness or fuzziness, fogginess, if you will, in the solution is enough to indicate that a precipitate has formed. So let's test ourselves. Let's figure out what kind of reactions these are, and then classify what they are. So the first one, you can see you've got C5H12 and O2 coming together. Well, probably this isn't too hard to figure out. This is going to be a combustion reaction, and the products will be CO2 and water. Now, all the carbon goes to CO2, all the hydrogen goes to water. Try to balance oxygen at the very end. So you can see here you've got 5 CO2s from the 5 carbons. Water has 2 hydrogens, so 12, and the original compound divided by 2 gives you 6 here. And the last thing to do is balance the oxygen. So from water, 6 times 1, plus from the CO2, 5 times 2, that's 16 oxygens. Oxygen is a diatomic, so 16 divided by 2, 8 O2s. The next one, HCl is an acid. And if you don't look any farther, you might be tempted to say, oh, acid base. But wait a minute, is PbNO3 a base? And the answer is no, all right? A base is a metal hydroxide, and a nitrate is much different than a hydroxide. So if you go a little further, you can say, oh, wait a minute, PbCl2 is a product, and I don't care about that, but notice the solid. So this one's going to be a precipitation reaction. The H and the Pb are trading places because they're alike. You'll end up then with Pb dancing with Cl. Lead is positive 2 in PbNO3, so it's going to be PbCl2 with negative chloride. H plus and nitrate, NO3 minus 1, come together. That's going to make HNO3, and you're going to need 2 of them. So for this reaction, you would need 2 HCl plus PbNO3. That makes the PbCl2 solid and 2 HNO3. And again, this is a precipitation. So notice that again, that this reaction did have an acid, but it's not an acid-base reaction. This PbNO3 is not a base. This would be a precipitation. The last one, HI, is an acid, H listed first. And LiOH, oh, this is a metal, lithium hydroxide. So this one is absolutely going to be an acid-base reaction. The H and the Li will trade places. We'll end up with water, H2O, and the other part will be lithium iodide, LiI. This reaction should look like this, and again, it's acid-base. So practice, practice, practice. The more of these you do, the better. You'll get better and better at them. People, again, usually do pretty good. And if you can recognize these reactions, you can answer people's questions in the hall when they'll think you're really cool. I'm letting you know all my cool chemistry secrets. I know you're thrilled to be here. Anyway. Okay, so that's the end of the Chapter 7, Section 7.1 lecture. I hope this has been helpful. If you have questions on anything, of course, you're welcome to reach out to me. Email is great. You can also talk to the Learning Success Center /Avid Center at Mount Hood Community College. All of us are here to help, so just ask your questions. Okay, hope you're having a great day. Thanks for being here, and good luck with your studying.